bottom symbol.
Okay.
So if you're trying to memorize this on your own, you've got that. You've got that option to do that. I don't have a good way to remember this. Cosine is always cosine, cosine, sine, sine. And then you figure out how to which sign goes in the middle. So it's just a matter here of plugging these into the formula. Cosine pi over 4, sine pi over 3, sine pi over 4, and then getting that sign right. So when it's minus, it ends up being plus in between.
Okay.
And you mentioned this, like, I think 2 lessons ago, you asked kind of like, well, is it a bunch of formulas? It's like, yeah, it is. It's really all it is. You just have to know which ones to use, how to put the numbers into the formulas and go. All right. Now, I know we talk about this like probably every lesson, but it's like, how well do you know your unit circle? And the better you know it, the faster, the easier it is for you to answer these, because these are all first quadrant numbers. So any improvement there on your unit circle? Any more comfort, knowledge, understanding?
Yeah, a little bit.
So like, you don't swim 800 meters all at once. You do it a little bit at a time. If you can learn the first quadrant, it will really, really, really help. You know, that a lot of these do go back to just the first quadrant.
Okay.
So that, like, if you're only going to learn one thing, it would be this. As a reminder, cosine is the x value and the sine value is y. So cosine pi over 3 is 1/2. Cosine pi over 4 is √2 over 2. Sine pi over 3 is the y value, which is √3 over 2. Sine pi over 4 is √2 over 2. Okay. And so from here, we will be simplifying. But one of the things that I've learned over the years of doing this is that the bottoms, the denominators are always the same on the left and the right. And that's kind of a check at this point. Like if you somehow had a 3 down here or something, you would know that you've made a mistake. These bottoms always end up being the same. So it's 4 on the bottom, square root of 2, plus 4 on the bottom. And then up top, √3 times √2 is √6. And so from here, you can combine the numerators, keeping the denominators. It's √2 plus √6 over 4. There's an error in your notes for the first one. Oh no, you guys are doing sine. Never mind. That is right.
Okay.
Apologize. It's like, why is it sine off? It's okay. I think the hardest step is breaking it apart.
Yeah.
And maybe the second hardest is like to memorize the formulas, but you've got to find a way to do that. Let's look at tangent 5 pi over 12 next. I mean, there's no value in this, and no one's going to ask you to do this, but you may be asked to do something where you have to break something apart into smaller tasks, and you may have to figure out how to change it so that it's more manageable. And that's kind of what it is here. We know that this is not a known value, but if you break it apart, it becomes a known value. So tangent's a little harder to memorize. But even before that, we got to decide, which of these are we using? So we got 2 pi over 6, 3 pi over 12, and then 4 pi over 12. And it's like, well, how do you get to 5 pi? Hopefully you can see you add the first two. This becomes tangent pi over 6. You always go back to the originals, plus pi over 4. And that's going to be your alpha and your beta. Did your instructor give you the tangent formula? Yeah, it looks like you got it. The one on the reference sheet I sent you is a little more compact. It's got the same kind of oddness with the plus minus. Let me snip that in here. So it's got this kind of oddity. It's like, why is there a plus minus? Well, the plus on the top, if the whatever the top symbol is goes with the top, and with the top, the bottom symbol goes with the bottom, and then the bottom there. It's just an easy way to remember it. This is alpha and this is beta. So you write the formula off to the right. You say, okay, it's tangent pi over 6. Don't try to evaluate it. Plus, because the top symbol, tangent pi over 4 over 1 minus tangent pi over 6 tangent pi over 4. Is that clear? Kind of
Yeah.
great. And so the steps your teacher gave you are good. Like I mean, I'd like a little more detail about how you actually rewrite a number. It's always a sum or a difference, and it's usually these ones to look at. Not always, but usually. And yeah, your teacher's pretty clear. You need to memorize your unit circle. It's doesn't sound like you're gonna get much grace on that one. You gotta know it.
Yeah.
Now tangent is not on the unit circle though, and that's kind of like an added frustration here. It's like, well, even if I memorize this, I still don't have it here.
Right.
Tangent pi over 6 is sine pi over 6 over cosine pi over 6. It's really, you think of y over x as being tangent. So pi over 6, you're like, okay, it's the y value. It's the 1/2 over the root 3 over 2. But you generally don't want to put that in. You really want to simplify it off to the side. Is that something that you would like us to review, how to simplify this?
Sure.
Okay. So 1/2 over root 3 over 2, you multiply by the reciprocal. Okay, so it becomes the 2's cancel, so you get 1 over root 3 over 1. 1 over root 3, you have to rationalize. You multiply the top and bottom by root 3, so you get root 3 over 3.
Okay.
So that all of that to take this position up here, but you need it down here at the bottom, so it wasn't in vain. Like you're going to use it a couple of times. It's worth getting it right. Plus 1 minus root 3 over 3. Okay, so now we got to find the tangent of pi over 4. So that's again, that's the y over the x, but at pi over 4, that's a nice one because y over x, they're the same. And that means it's just 1. So if you do enough of these, you're like, oh yeah, tangent pi over 4, it's 1. I don't have to do anything special for that.
Got it.
So thus far we've just been analyzing, evaluating, putting in the values, and like you could like if you're like, hey, this is as far as I want to go in this problem, like this is correct, but you're probably looking at like 7 out of 10 or 8 out of 10 because you didn't simplify. And this is as much a problem or a challenging problem as the rest of it. Just knowing what to do. Did your teacher give you any hope or message for this? Like, hey, you don't need to simplify, or it's okay to leave roots in the bottom, or is it total full simplification?
I think it's total.
Wow. Yeah. Okay, well, let's talk about how to do that. So there's and I'm just going to reset here because it's kind of its own problem, and it's one of those you'd give to an algebra 2 student and say, all right, here you go. It's complete problem here. So the top and the bottom, you want to make a common denominator, which is going to be 3.
Okay.
It just happens to be the same in this problem. It's not always. So in your numerator, it's root 3 plus 3 divided by 3. Okay, and that's just me combining the numerators all in one step. Same thing down here in the bottom, 1 minus root 3 over 3. Now, when you multiply by the reciprocal, oops. When you multiply by the reciprocal, the threes cancel. Okay, and it's actually always the case. Like if you have something on the bottom, but they're the same, you can cancel these. You don't have to show this multiplication by the reciprocal, but it's already done here. So here's where we're at. It's root 3 plus 3 from the top left over 1 minus root 3 from the bottom right. And then obviously on the bottom here, these all cancel. But we're not done because you cannot have no roots in the bottom. So you're like, darn, I really thought I had this all done. Nope, there's more. This is where you multiply by the conjugate. The conjugate is 1 plus square root of 3. It's the change in operator. Okay, so on the top and the bottom, you FOIL. On the top, it's root 3 plus square root of 9 plus 3 plus 3 square root of 3. On the bottom, it's 1 plus root 3 minus root 3 minus the square root of 9. All right, so in the numerator, we know that root 9 is really 3. And we have 1 root 3 and 3 root 3, so that's 4 root 3s, plus the 3 goes with the other 3, that's 6. On the bottom, positive root 3 minus root 3 is 0. This is 3, so it's 1 minus 3, it's negative 2. But wait, there's more. You have to divide each of these by the negative 2. So it's minus 2 root 3 minus 3.
Got it.
And it like, now if you didn't believe me, now you're like, wow, this really is like a whole new problem. And a lot of students really hate that about this. They're like I mean, like this is as much work as what you were doing up here. So, is it 7 out of 10? Is it 8 out of 10? I don't know. Maybe it's less. Maybe it's 6. You should ask your instructor. You should say, can we leave it like this? Do we need to work it all the way through? It does add a lot of time to the problems.
Yeah.
Yeah, it's not great.
No.
Okay. So now let's look at these sum and difference identity problems. Let's look at number 2. That's probably a good use of our time. These are not great. These are really, really lengthy. Unless you have specific problems you want us to work on.
No.
Okay. So I chose this one because it's got both a sine and a cosine sum and difference formula in it. I'm gonna grab, we'll do the sine one first. Do you have multiple whiteboards in your classroom at the front?
Yeah.
Sometimes these are the kinds of problems that go on to like multiple boards. There's like so much going on. So in this one, your alpha is 7 pi over 6 and your beta is x. And we're gonna use this formula down here. So it's sine 7 pi over 6 cosine x. Got to decide whether it's plus or minus. So whatever the sign is here, it's positive on the top. You use that one there. So plus, okay, and then it's cosine 7 pi over 6 sine x. All right, now the next part here is to look at the cosine. So let me grab that formula. I think it's really good to see the formula underneath it, and grab that cosine formula. All right, and then let me just snip that one more time. All right, so in this problem, alpha is going to be 2 pi over 3, and beta is going to be the x. Waiting on a little technology issue. There it is. All right. So alpha and beta, notice I'm labeling them kind of like x1 and y1 each time. And you've got cosine 2 pi over 3, cosine x. Because it's plus, that's the top operator. We're going to use the top operator there, minus sine 2 pi over 3 sine x. Now, very important, this minus in the middle. It's easy to like doing so much to forget that that minus in the middle, it comes down and it's all of this that's being subtracted. So one time I had a class where in college where a student came in, he actually rotated his paper. We were doing a different class than this, but it made sense because of how little room there was when you hold it vertically. So it's okay to kind of rotate if you think that helps here. Knowing your unit circles, super important again. We're just reading off the values for sine and cosine based on the quadrant that you're in. Excuse me, let me snip that in here. Where am I going to paste this? I guess we'll try there. Okay. And I pasted the wrong quadrant. Okay. All right. So 7 pi over 6, sine is the y value. So it's minus 1/2 cosine x. The x value is minus square root 3 over 2 sine x. We'll deal with the minus in a moment. Cosine 2 pi over 3. That was in the other quadrant. So, the unit circle now, it's like you have to know it. It's so hard to do these without it. Some students flip their exam over and they'll do it real quick at the beginning. That way they're looking it up each time rather than trying to calculate it. Just becomes a lot here. So 2 pi over 3 minus 1/2 cosine x. And then minus sine 2 pi over 3 is minus root 3 over 2 sine x, like that. And while this looks bad, when you distribute in the negatives, which we're going to do now on this same line, it becomes plus 1/2 and plus root 3 sine x. And you'll see that they're all opposite in sine. Those are opposite in sine. The cosines and now the sines are opposite in sine. And everything cancels out to 0. Any questions on that?
No.
All right. We can do one more of these, but we should move to some solving at some point. This number 6 kind of comes to mind. I noticed, and it's a question for you here at some point. Your teacher put on your other worksheet that we looked at last Wednesday, there was like one of these like known Pythagorean identities. And some teachers really like to put those on tests where it's like to prove the thing that's given, like prove that 1 plus tangent squared x is secant squared x. And that's kind of what this is like. This one on the right is a double angle. Does your teacher tend to give those types of problems or emphasize those, like prove the thing that you already know on a test?
Yeah.
Okay. So this would be, that type of problem here. It's really no different than the ones we've just been doing. You need the sum and difference formula. Okay, so where the instructor could be problematic is they could give you the problem like this, and then you have to know, oh yeah, it's really sine x plus x. Like you may have to figure that part out on your own when you're doing this. So if we grab that formula, this one's more of an algebra exercise, but it's it's like maybe hard the first time you see it. So that because it's plus, it's gonna be plus on top here. So it's sine x cosine x plus cosine x sine x. And so sometimes you need like some words because you're like, what, like these, why does this make two? It's because if you reorder the ones on the right, sine x, cosine x, or multiplication can be done in any order, you see that, oh, I've got one here on the left and one here on the right. That makes two of them. And so a problem like this would tell you, it would say like use sum and difference formulas. You are not allowed to just say, oh yeah, it's a double angle formula. I know that, and be okay with the formula. They want you to work it out.
Okay.
So if you don't mind just looking at these questions real quick, the sum and difference identities practice 1 through 4. I'm going to snip that in. Any of these stand out that you would like us to do? We could even just separate them into the two quantities if needed. Like how do you make 11 pi over 12 is what I mean. How do you do that? That's the kind of question you might have on a test, how to break that apart.
Yeah.
So we go, sorry, go ahead.
Um, how would you do the number 2? Break that apart.
Yeah, good question. Because like, well, like, what is even going on here? Uh, the idea, a little bit of the idea is that to get something in the second quadrant, you generally need like to take one from here and one from here. Since this one's in the third quadrant, it might require one from there and one from the previous or one from the previous. And so it is literally a bit of a guessing game. It's like saying, well, do any of these work out nicely? Like for example, 7 pi over 6 is really 14 pi over 12. Okay, and that gets you really close. You're like, okay, 14 pi over 12 plus, well, I need to add to it 3 pi over 12. So what is 3 pi over 12? Well, it's pi over 4. Oh, that's good. That's good. That's one I know. And same with 7 pi over 6. So this one here, which is in the third quadrant, which that may be its own challenge to figure out. But you can see it took one from the quadrant and one from one of the other quadrants. And it's kind of a bit of a guessing, like, how do I do this? 19 pi over 12, you can say, okay, well, I'll start with 14 pi over 12. Plus I need a 5 pi over 12. Well, that doesn't work, okay, because you don't know that one. So then you kind of increment in that quadrant. You're like, all right, well, what's the next one? What's another way to get there? So these aren't necessarily easy to come up with. So like if you go to 5 pi over 4, let me write that somewhere, 5 pi over 4, that's 15 pi over 12. Oh, then you're like, oh, that's a little better because I can add 4 pi over 12 to that.
Right.
And that one's like, oh, that's works. That's pi over 3. That's good. That's 5 pi over 4. But again, it took one from the third quadrant and one from the first quadrant to figure it out. And there's not really it's sort of it's like, remember those problems a long time ago? It was like, find two numbers that add to 30 that are maximum when you multiply them. Like, you eventually learned a formula, but you could also just guess and check pretty quickly. And we sometimes don't realize, like, there's probably enough time to just quickly guess and check and then move on to doing the problem. We don't have to like rush to get an answer right away. Okay, so if those are clear, I'd like to do some solving problems again. These seem to be new-ish to you.
Yeah.
They do rely on your unit circle. So let's take a look at 9. Let me know when you're all ready here for us to get going.
I'm ready.
Great. So the governing kind of the overarching thing here is like, can you get the trig function isolated? Okay. And you can, right? It's tangent squared theta equals 3. But is that really isolated? And the answer is no, because it's really there's a square there, so you undo a square with a square root, but you have to remember it's plus or minus. So tangent theta equals plus or minus square root of 3. Now, this is not on the unit circle. Like if you go and look at your unit circle, there's no place where there's a square root of 3, and that's because it's tangent. Tangent is always y over x. Okay, so you have to kind of know, well, how do you even get a square root of 3? You get a square root of 3 by doing square root of 3 over 2 times 1/2. That's the path to getting square root of 3. If you end up getting 1 over the square root of 3, or even root 3 over 3, it's the flip of these. It's 1/2 over root 3 over 2. So you kind of have to know that to be able to map through this. So you're looking for where the y value is root 3 over 2 and the x value is 1/2. And you see on your unit circle that this happens in a lot of places. Let me grab the unit circle here. So you can see that it happens here at pi over 3. It's got the y value root 3 over 2 and 1/2. And then similarly, 2 pi over 3. Okay, but you want the angle. You want to make sure you grab that. And then down here again at 4 pi over 3. Nice little pattern there. And then again at 5 pi over 3. So your answers are pi over 3, 2 pi over 3, and 4 pi over 3. And the reason we're not being more concerned about the sign is that it's both plus and minus. So the 2 positives make the plus, the 2 negatives make the plus, and then 1 positive, 1 negative gives you the minus. However, there is a bit more to this. The last problems we had looked at, your teacher wrote this 0 to 2 pi. These do not say that. Did you guys cover the infinite period, kind of the fact that you have to say that these go on forever?
No.
Okay. All right. Well, we'll exclude that for now. It's kind of it's another like little extension to the problem that makes it, all the more frustrating. So, okay, let's look at number 11 and then 12. 11 is one of these where the period has changed, and that does affect the answers. Affects it quite a bit. All right. When you look at this problem, it's kind of already solved for the trig function. Like it's already kind of there for you, except it just happens to be this x over 2. So a lot of times you'll see a substitution made. You just write as theta is x over 2, and you say, okay, cosine theta equals root 2 over 2. And you go to your unit circle and you figure out, well, where is the x value root 2 over 2? And you end up that it's there and there. It's pi over 4 and 7 pi over 4. So like the solution to this problem, this cosine theta equals root 2 over 2, is pi over 4 and 7 pi over 4. But it's a big but, like that's not what we're solving. We're solving this one up here. Okay, so you have to know that while you solve this problem, it's not really this solution. You're like, well, what do I do? Well, you start by writing your answers. Pi over 4, 7 pi over 4. You just say, okay, if it was theta, these are my answers, but it's not. And so you back substitute. You say, oh, it's really x over 2, which is now equal to pi over 4, x over 2, which is equal to 7 pi over 4. And then you solve for x. So what I mean is you're going to clear that fraction. You're going to multiply both sides by 2. So x is 2 pi over 4, which is pi over 2. And then similarly over here on the right, you get x is 7 pi over 2. Now, if you didn't notice, the answers got bigger. Okay, and there's kind of this thing where it does depend on your period. Like most teachers tell you to do it on 0 to 2 pi. Either the teacher didn't know or they just didn't put it down. But that actually eliminates one of these answers. So remember at the end of last semester, we had to check our answers. We had to see if it was extraneous or not. It's the same thing here. This is now extraneous because it doesn't fit the period. It doesn't fit in this interval, this domain. 7 pi over 2 is 3.5 pi. That's way too big. So this would be your only answer.
Okay.
So the kind of the summary of this problem is that you tend to have to cancel out answers when there's a fraction in here. So if it was like x over 3 or x over 4, you would have to cancel answers. That also should tell you that there's something else going on when the number is, when it's like a whole number inside there. And we'll see that in number 12. So like if it was 3 times x or 5 times x, that is a different type of situation. Right, now this has a couple of other added little things in there. We should add 1 to both sides. We should divide by 2. So it's cosine 3t equals 1/2. And rather than focusing on this 3t, you make a substitution. Say, okay, well, let's let theta equal 3t. Cosine theta is 1/2. And that's where you go to your unit circle again. And you ask yourself, where is the x value 1/2? So pi over 3, and then 5 pi over 3. So those are your answers. You're like, okay, I mean, know what to do here. Like, right, theta equals pi over 3. Theta equals 5 pi over 3. I know that it's not theta, it's really 3t. Put 3t here. 3t here. Okay, and then you divide both sides by 3. So you get t equals pi over 9. T equals 5 pi over 9. You box it in and you feel really good. You're like, oh, I understand it. I feel really good. And then you get your score back on this problem and it's like 5 out of 10. You're like, what did I do wrong? I did everything right. Well, just like the last problem, when the period changes, in this case, when there's a whole number in front, you have to add answers. And so you're missing some answers here. And you're like, how am I supposed to remember all the stuff would think would come to mind? And I don't know. This isn't, you know, this isn't great. But that's where you got to talk to your teacher and ask like, are these really the types of problems I'm going to see? Or, is it okay if I just give you these two answers? Because you're really supposed to go out based on the changing period. All right. And there's a couple ways to do it. What I like to do is just keep writing the answers. So like it's not that pi over 3 is the answer. It's pi over 3 plus, if I go all the way around again, plus 2 pi is also an answer. And that's 7 pi over 3. So I look at now 7 pi over 3 as an answer. And when you divide it by 3, you get 7 pi over 9. And that's okay. That still fits within this 0 to 2 pi window. And then I do it again. I say, okay, well, let's go out another 2 pi. Let's go out 4 pi. Okay. And that's 13 pi over 3. And that's okay too. 13 pi over 3 divided by 3 is 13 pi over 9. And that's okay. Make sure I'm doing this right. Yeah. So, for this one, there's actually quite a few answers. And you can end up start seeing the pattern here. It's 1 pi, 7 pi, 13 pi, but 19 pi over 9, that's too big. That's greater than 2 pi. But that's only for this top answer. We then have to do it for this bottom answer. We have to then add 2 pi to it, or 6 pi over 6. So it's 11 pi over 6. Sorry, 11 pi over 3. So you say, okay, well, it's really 11 pi over 9. And you can pattern it. If you recognize that it goes with the 5 pi over 9, 11 pi over 9, you can get the other one. But if you're not sure, you just go back. You're like, all right, now let me add 4 pi. And you're like, okay, 4 pi is really 12 pi over 3. So that's 17 pi over 3. And then when I divide that by 3, it's 17 pi over 9. That's okay. The next one we would exclude. I'll write it out here. It ends up being 23 pi over 9. But these are all your answers. These are all your answers. So what you want to be looking out for with that period change, you really want the one where the period is a fraction, because then you cross out answers. And notice we only had to cross out one. When it's a whole number in front, you end up adding a bunch of answers to it. Give me some feedback. What are you thinking? What's kind of going on as you
So it can be, they're all in like one quadrant, but it can't exceed 2 pi.
they're all in the unit circle,
Yeah.
but you have to keep going because these are still valid when you change the period. See, like what's probably not being shown here is, the graph of cosine looks like this. So if
Yeah.
we ask where it equals 1/2, you're like, oh, it's right there and right there. But here's what happens when you change the period. Cosine now looks like this. So now there's 1, 2, 3, 4, 5, 6, 7, 8 answers. And that's what's literally happening when you make that period change.
Right.
And same thing goes the other way. If you stretch it, it doesn't have as many. If you stretch this thing, and your cutoffs here, well, it only had one solution. All right, so in the limited time we have left here, let's look at this graph problem. I was going to say the same, but I'll just say it now. It is you probably want to redo the ones we did together if you have time at some point before your next class. Just doing them once will really help, your understanding if you got the time. Okay, graph, cosine function. Okay, this is kind of random, but this is something that's important to do. Can you tell me the amplitude of this graph? Any idea about the amplitude, Paige?
2.
It is 2. Good. Phase shift is pi over 2, but we have to specify the direction. Because it's negative, it's to the right. And what that means is rather than starting your cosine at the origin, meaning like here, you're actually going to go out, you're going to move everything out to the right, that amount. The period is always 2 pi over b when it's written in this form up here. The number in front of x is 1, 1x. So it's 2 pi over 1 or just 2 pi. So that's good. Like that's a standard cosine. So normally, let me draw the parent function here and let me make this 1 and -1. So the normal parent function for cosine looks like this: starts high, low, comes back high, like that. But the only thing that's changed for us here is the amplitude and the period. So I'm actually going to go up a little bit more, just to make this more pronounced. I'll do it in red. So the red, the period change, all it does is pull the points. Come down, go back up. And then the last thing is this phase shift. So anything out to the right, it just pushes everything right. So each unit just pushes out to the right pi over 2, pushes out to the right pi over 2, pushes out to the right pi over 2, pushes out to the right pi over 2. And these arrows kind of make it like, okay, yeah, it's just moving out in that direction.
Okay, that makes sense.
All right, so let me just stop the recording here.